This chapter is a very brief introduction to some of the most important fundamentals of communicating ideas using visual signs. There's some very basic principles that if you keep in mind as you design your visualizations, they really become essential and valuable as you make your own, design your own visualizations to present your own data. And you'll find that there's some very simple things you can do that I think will help tremendously. So the first, and probably one of the most often overlooked ideas, is the concept of the grid system. So this is a page that I've taken from Josef Müller-Brockmann's extensive book on grid systems. And what you can see here is he's laid out the idea of how a grid organizes data when it's presented on a page. And what you can see here is that the information is organized into columns. Each column is left justified to each of the different grids. Excuse me. The margins between the grids are all the same size, and the line height is the same size. Now, this gives incredible meaning and organization to what's being presented. So first of all, you'll see that the eye very naturally flows across and down each one of the columns. Separately, following that Gestalt principle that we talked about before of proximity, things that are in the same column, our mind reads them as having perceived similarity of meaning. So you can see how the grid system is utilized by a newspaper like the New York Times to present what is truly a very dense amount of data. And one of the reasons that it makes sense is because they have so strictly enforced the grid. There's another major principle that the New York Times is abiding by here. And it's something that we can find when we go back even to ancient Egyptian papyrus. And it's this idea that's called hierarchy of size. And in this beautiful scene taken from the Egyptian Book of the Dead, the most important figures are the biggest. And so what you see here is in the center on the bottom row is the god Anubis. And Anubis is twice the size of the human being on his left. Now, we interpret this in modern times not to mean that Anubis was twice as tall as a man, but that he was twice as important as the other figures. And you'll find that the people on the left, who are the same size as the gods, are the rulers. So this hierarchy of size is imposed also in the New York Times, where you'll see that the main, what is the biggest visual item on the page? Well, it's the headline, right? It's the New York Times logo. What's the second biggest thing on the page? It's the central image and the central column. So your eye is drawn to the most visually dominant aspect of the page. It's another reason why making things large gives them more meaning. So the idea of hierarchy of size and grid are really being strictly enforced by the New York Times. What are some other basic elements of visual communication? Another one of the most common is this idea of grouping. And you can see how this appears in the periodic table here. And very often, one of the most important parts about the periodic table is the way that the columns themselves are organized. And what you have on the left are all of the metals. And what you have on the right are all of the non-metals. And in the middle are all of the transition metals. And on the very bottom is the lanthanum series. And these groups are given meaning by being next to one another. In other words, it's very clear that hydrogen and lithium share a common quality by being in the same column. There's one additional principle that I think is very, very often overlooked in scientific visualization. Tufte brings this about, and he calls this idea 1 + 1 = 3. So let me explain. Let's take a moment. Look at the screen and tell me what you see. I think most people would say they see two lines. Let's go again. Now tell me what you see. I think most people consistently say, I see two lines. Let's do it one more time. Now what do you see? Most people will say, I see two lines and a space. It's very much like the two lines now create a road through this graphic. Essentially, the content is the same, but the spacing is different. And there's a perceptive psychology effect here, and Tufte calls this 1 + 1 = 3. And what he means is that even though you have two graphical elements on the page, what you really have to pay attention to is the third graphical element, which is the negative space that's created between two strong graphical elements. So when you create lines, what's very important is that you realize that you're not just drawing a line, but by dividing space, you're creating all the negative space around it. So it's very easy in drawings for us to create many lines that all call for our attention. So what is one of the ways that we can offer understanding the principles of psychology and perception for how to minimize something like this? Well, let's look at what Tufte would call reduction of noise in this classic box and whisker plot. So very briefly, the plot shows a number of categories along the x-axis. What you see is the max and min values along the lines, and then the box, and those are the whiskers, and the box shows the standard deviation, the majority of the 95%, and the line in the middle shows the median. So this is a traditional scientific graph that really came out of Tukey in the 50s. So what is it about this graph that really confronts this concept of 1 + 1 = 3? Well, Tufte has another idea that he calls the graphical integrity. The main idea is that every line in a visualization should convey meaning. And you should convey meaning in the most compact form possible. So let's take an example. What are lines that don't need to be on this screen? Well, let's take the most obvious ones. The first is the background lines. They don't really need to communicate what can be shown in the very small little ticks that are now placed on the left. And it reduces the graphical noise significantly, and it doesn't change the meaning at all. Well, let's continue to reduce. What are other lines on this page that we don't need? Well, very often you'll see that scientists will create figures in boxes, right? But the box very clearly violates this principle of 1 + 1 = 3. Because what does it do? It draws attention to the box. What you really want to pay attention to is the data. So how do we get rid of the box? We can very simply remove the top and the right, which don't add any meaning to the figure. So if you're learning anything from this, think about the graphs that you're drawing and how much additional line they are including for the data that they communicate. Tufte goes even further, and he says, you know what? The box is a two-dimensional box, but what it's really communicating is the top and the bottom point. And the line is a point. It doesn't need to be a line. So if we want to reduce this even further, we can actually remove the box entirely and replace the midpoint with a dot. Now you have a graph that has no less meaning and far less ink. In the way that Tufte describes data graphics, this is a high value for us to strive for. Another thing that we can do that really allows us to focus on this idea of 1 + 1 = 3, look at each one of the graphical lines here. They're really significant. And when you look at the image, you don't just see the data, you see the line. But the line is really pointing you just to the end points, right? What it's really showing you is the top line is showing you the maximum data point and the top of the standard deviation. So what if you also diminish the intensity or the width of each line? And now what you do is you've taken very thick lines which draw attention to themselves and made it so that what you're paying attention to are the endpoints of the lines. So you can even further reduce the noise or the ink necessary to communicate the number of data points in a graph by turning down the intensity of the lines. Tufte talks about this as expressiveness. What's important is that data graphics are expressive. And here I've chosen McKinley's description, which is the idea that visual graphics need to express all the facts in the data and only the facts in the data. This is something that's very easy to do, to accidentally violate. And I'll give you a quick example. So here you see a data set that shows you the relationship between a different number of car manufacturers and the country in which they're manufactured. So look at this graph. What is wrong with it? So you see that you can easily look at this and tell that the various cars come from different nations. But what's misleading about this graphic? Well, what's misleading about this graphic is the bar communicates an idea of a continuous value, and that the bar for Honda is bigger than the bar for the ACM, for the AMC. And actually, there's no quantity communicated in each of these values. And a better way for us to represent this fact would be by showing points. What we actually have is that we're mapping nominal values, right? Category labels, which is the country or the origin of the manufacturer of each car. And nominal values don't have magnitude. So when you show them using a bar chart like that, you give the false impression that there's meaning in the data that implies a magnitude that's not there. So this graph is not expressive in the way that McKinley describes it, because it's communicating information that's not actually there. Another thing that Tufte talks about with his idea of data ink, if we're going to make the graph have as few pixels as possible to communicate the most meaning, what is the furthest possible way that we can go is what Tufte calls chart junk. And chart junk is a wonderful example of how data graphics appear very often in popular culture, in magazines. And they're designed to give this huge emotional impact. Like you can see in this graphic, what's trying to be shown by the newspaper is this idea that the costs of elections are becoming monstrous. And so they have this Tasmanian devil serpent, and the teeth of the devil serpent represent the spending levels, and they're going up. But if you look at the graph to the right, what's represented is the same value empirically. So in the way that Tufte represents graphics, the graphic on the right is the more meaningful graphic because it communicates the same data with far less editorial, right? Far less unnecessary graphical marks. Now, what's also important to note is, while I think Tufte is a purist in the way representation should include meaning and only meaning, experiments have shown that readers remember infographics with this kind of emotional content better. So as a designer of graphics, you'll have the option of deciding the faithfulness of the representation. So what I hope comes clear to you from this particular chapter is that there are a number of ways that you can choose to represent the data, and that they are small changes can give you significant multiplier in the organization and the legibility of your graphics, as well as their integrity. And I hope that you feel more well-equipped to make decisions about how to decide how to encode particular kinds of data.